Mercury Optical Lattice clock. So today I will present you the latest results and how we implemented a 2D MOT to improve the Mercury Optical Lattice clock. This is the outline of my talk. So in the first part, I will show you the latest results and the current situation of the Mercury clock and where are our limitations. Then I will present how we implemented 2D MOT. And in the third part, I will discuss the benefits of the 2D MOT, especially on the stability. And finally, I will discuss the future and the perspectives for the clock. So in the first part, in our case, we are using the mercury atoms. So why did we choose the mercury atom? So the mercury atom has a suitable alkaline Earth-like atomic structure that is reminded on the right here. And the main point of using mercury is its weak sensitivity to the blackbody radiation shift. It means if we are able to control really well the temperature in the lab, this shift will be lower than the other atomic species. And I reminded some numbers here. So the shift is 60 times less for the mercury than in the ytterbium and 30 times less than in the strontium. Mercury has also 7 stable isotopes. And one very important point for us, it's the high vapor pressure of the mercury. Indeed, it allows us not having an oven. And also, it's easier for us to implement a 2D MOT. On a more fundamental physics part, the mercury has been little studied in the cold and ultra-cold regime. And it's also sensitive to the potential variations of alpha, the fine structure constant. Despite these advantages, there is drawbacks using mercury, and the main drawbacks remains in the wavelengths. Indeed, all of our wavelengths are in the UV. So here in the scheme, I showed in purple the clock transition that is at 265 nanometer, and in the red, the cooling transition with our 3D MOT that is at 253 nanometer, and it's the same for the lattice laser that is in the near UV. And on top of that, we also have potential nonlinear lattice effects that are added. Here is a scheme of our clock. So in the center here, there is the science chamber in which are probed, cooled, and trapped the atoms of mercury. So in the first part, we cool them thanks to an ytterbium fiber laser that is doubled twice to produce the 254 nanometer beam. Then we can trap the atoms in the trapping laser, that is the lattice laser. And finally, when these atoms are cooled and trapped, we can probe them with the clock laser. So it's an ytterbium fiber laser that is pre-stabilized on the ultra-stable cavity. This cavity is a 10 centimeter cavity that flickers at 4 or 5, 10 to minus 16. Then we quadruple this laser that is in the IR to produce the 266 nanometer. Here was the latest uncertainty budget that was published by the group in 2016. So as you see, we are in the low 10 to minus 16. But what you directly see looking at this uncertainty budget is this main term, the lattice light shift linear, that is really the main contribution to this budget. So what are the other limits for this budget? So the stability for these measurements, when it was taken, it was 4 10 to the minus 15 at 1 second. And several aspects were explaining this relatively high stability. So first, we had a small number of atoms in the lattice. So one solution could be to increase this number of trapped atoms. And as a consequence, we will increase the signal-to-noise ratio. On top of that, these atoms were in too few number, and it was captured in a too long time. So one solution could be to decrease the cycle time, and I will explain later what we decreased. And as I showed before, the linear lattice light shift was too high, and what we implemented was a new locking scheme for the lattice laser. We locked it on an optical frequency co. And so a solution to, at the same time, increase the number of atoms and to decrease the loading time, we decided to implement a 2D MOT. So here I present you the clock cycle. So a clock cycle, when we run the clock, we have several steps that are repeated again and again. So the first step was, as I said, loading the atom. We cool them with the 3D MOT. Then we trap them with the lattice laser. Then we have 2 atoms in 2 Siemens states. We state select one of them that goes on the upper level. Then we apply a push beam to blow away the atom that stayed in the bottom level. And we proceed to the probing of the atoms with a pipe pulse. And finally, we detect the atoms that are back in the lower level. And again, we repeat this cycle. So concerning the timing, as you see, for a clock cycle that is close to 1 second, the main contribution of this cycle is the loading part, that is around 800 milliseconds. That was 800 milliseconds where the uncertainty budget was taken. And so a solution could be to reduce this loading time. One can ask, what about this probing time that could be increased? Because of course, if we increase our probing time, the spectroscopy would be an hour. But in our case, we notice that by increasing this probing time, the lifetime of the atoms in the lattice started to be limited for us and producing atomic fluctuations that had a direct influence on our stability. So the only part I did not mention before was the 2D MOT laser here. In fact, it's the same system as the cooling laser, except that it will be a 2D MOT laser. So a few words about the 2D Magneto Optical Trap principle, presented by Dickman in 1998. So it consists in 2 reflected beams, so in 2 directions, so instead of 3 for the 3D MOT. And on top of that, we add a magnetic field gradient to trap the atoms. So here there are the coils in the anti-Helmholtz configuration. It provides us a quadruple magnetic field. We chose 2 directions here, and we constrain the atom in this direction. And here are the MOT beams. And our atomic beam is only constrained on 1 direction. Here is a picture of the Magneto Optical Traps, so the 3D MOT part and the 2D MOT. On the right of the picture here, there is the mercury source. So we just cooled the Peltier module on which there is a drop of mercury. The vapor goes into this chamber. Then the 2D MOT is applied. So as you see here, it's in the Z direction and the Y direction. You can see the windows here. For now, we are only using 1 window. And then once it's constrained in 1 direction, it is sent in the 3D MOT chamber. As you can see, there are the arms here in this direction, this one, and this one, where they are trapped. Here I show a transversal cut of the scheme. So on the left part, there is the 2D MOT part. The 3D MOT chamber is on the right. And in the middle, there is a low conductance section to bring the atoms in the 3D MOT parts. And here you can look the windows we are using. Concerning the size of our 2D MOT beams, it's close to 1 centimeter over half a centimeter. Now I will say a few words about the 2D MOT locking setup. So the 3D MOT, to cool the atom, is locked thanks to the saturated absorption method, so on a mercury cell here. And because we are using the same system, the 2D MOT laser, we decided to frequency lock the 2 seeds, the seed of the 2D MOT on the 3D MOT, thanks to frequency to voltage converter. And with this scheme, there are few parameters on which we could play. So the first obvious one was detuning towards the 3D MOT by only modifying this IOM here. A second parameter on which we could play was the magnetic field gradient of the 2D MOT. A third parameter on which we could play was the power of the 2D MOT. And finally, the last parameter was the shape of the beam. So here on the first graph, I showed the effect of the detuning. So on the x-axis, this is the absolute detuning in gamma, gamma being the natural line width of the cooling transition. And on the y-axis, this is the atomic count, proportional to the number of atoms that we trapped. And we see that when we detune our 2D MOT, we observe a maximum here. So as a consequence, we decided to run our 2D MOT around this detuning, and you see the symmetrical behavior of the effect of the detuning. So the second parameter was the magnetic field gradient here in the x-axis. And the same principle was observed. We had maximum here, and we decided to operate a 2D MOT at this level. So the figure was not symmetrical, by the way. And the last effect that had the more influence on our 2D MOT was the power of the 2D MOT. So here, the x-axis is a bit different. This is the loading time. What we see is that the more we load atoms in the MOT, the more we have atoms. So in the blue curve here, the 2D MOT is not on. So you see the usual effect of loading more atoms in only the 3D MOT. Then we decided to put the 2D MOT on and to increase again and again the power. the first thing we see is that we see an increasing, and the more we increase, the more we have atoms, except that at the end, when we compare these two curves, we sort of observe a saturation. I will say a few words a bit later. So this graph allowed us to choose between two configurations. Usually we run the clock with 800 millisecond loading time here, and we see that with the same loading time, we were able to have more than three times the number of atoms. So we could decide to run the clock with more atoms, or we could decide to run the clock with a shorter loading time, for example here, and the number of atoms would be still higher. But as I said, at the end you observe a sort of saturation. That's why we need to work on the beam size. We did not do it for now, and possibly use more beams, because as I said, we are only using right now one window, so we can expect that by using more beams in these different windows, we could have even higher results. And so now, what were the benefits of putting this 2D MOT in our Mercury optical clock? So as I said before, the benefits of the 2D MOT were the increasing of the number of atoms, and it was possible to divide by more the loading time. The direct effects were observed on the Deke effect. So in our case, we cannot proceed to synchronous because we have synchronous operation of the clock. And that's why we had to determine what was the Deke effect in our case, was it limiting, and what the 2D MOT allowed us, if it was possible for us, to decrease this Deke effect. So the Deke effect has two contributions. The first one here is the laser noise contribution, so it concerns our microscopic oscillator. And this right term here in the formula concerns the clock sequence contribution. In our case, we are performing a Rabi, this is a Rabi cycle time. And what we decided to see was, in x-axis, the loading time, and in the y-axis, the Deke effect comparing to this loading time. And what we see is that usually we're operating the clock with 800 millisecond loading time, and what we saw is that, of course, when we were decreasing this loading time, the duty cycle of the clock was better, was higher, and as a consequence, the Deke effect was smaller. We were able to run the clock at 500 millisecond loading time, and even at 300 millisecond loading time. So this Deke effect was not limited for us, because it could have been here. So to see the effects of our 2D MOT, so it allowed us to increase the number of atoms. It was possible for us to decrease the cycle time, and the compromise that we chose was to increase the loading rate. The consequence on the stability was this one. So just to remind you, the uncertainty budget was taken with the 410 to minus 15 stability. And here you can see a stability that is probably below 7 to the 10 to the minus 16. Why below? Because we are only comparing against ourselves, and we start to be limited by our cavity. So to determine precisely our stability, we will probably need to compare with other clocks at the lab, and especially the strontium clock. So to conclude, we added a 2D MOT that increased by a factor of 5 the number of atoms, maybe more if we manage to work on the beam size of the 2D MOTs. We're able to divide by 2 the cycle time, and this new stability configuration is promising for comparisons of clocks over Europe. And with that, I thank you for your attention.
So, thank you very much. Very nice presentation. Do you have some questions for our speaker? I have a question about, so to improve the stability, you discussed the amount of atoms that you trap in your system.
Mm-hmm.
Is there a limitation caused by the clock laser stability that plays a role in this as well? Or could you get more improvements, say, if you have a better probe laser system?
If you have a better laser system, yeah, because it would be possible to, basically, in the Deke effect we had, there is this laser noise contribution here. Yes. So yeah, our laser is 10 years old, the clock laser, so probably the new generation of laser could have an even lower noise for laser. So yes. Yes.
So if you go back to your loading time plot, the number of items.
This one?
The loading, the number of items. Yeah, this one.
Okay.
It seems like there is like, I would expect like, if the flux is constant, I would expect this to be exponential, but at around 150 milliseconds, there is a kind of jump.
Yes, we observed this jump. We tried to see if it was at first a problem in our measurement, but yeah, we observed that, and we did not understand why we observe at low loading time this kind of behavior. It was
Any other questions? If not, well, let's thank the speaker again.